All right, let's talk about something we all use every single second we're online, but maybe don't think about too much: digital encryption. This is the invisible shield, the silent guardian that keeps our entire digital lives private. So, let's jump right in and see how it works.
You've seen it a million times, right? That little padlock up in the corner of your browser. We all know it means safe, but what is it actually doing? What's going on behind the scenes to make that little icon appear? Well, today we're going to pop the hood and find out exactly what makes that lock work.
So our story starts with the absolute workhorse of modern encryption. It's a system called AES, and the best way to think about it is like a high-tech, virtually unbreakable digital lockbox. It is the gold standard for locking up data today.
Now, what's so cool about AES is that it wasn't just invented in some secret lab. It was actually the winner of a global competition. Back in 1997, the US government basically said, "Hey world, we need a new, super strong way to encrypt things. Send us your best ideas." After years of public tests and attacks, a Belgian design called Rijndel came out on top, and it became the AES that we all rely on.
So what kind of thing is AES? Well, at its core, it's what we call a symmetric block cipher. Now that sounds technical, but the idea is actually really simple. Symmetric is the important word here. It just means you use the exact same secret key to both lock the information and to unlock it. One key does everything. Easy, right?
Digging just a little deeper, here's the game plan. AES grabs your data, chops it up into these fixed-size blocks, and then puts it through round after round of seriously complex mathematical transformations. It just scrambles it into complete gibberish. And you can choose how strong you want it to be. The longer the key, like 128 or 256 bits, the more rounds of scrambling it does, and the tougher it becomes for anyone to crack.
Okay, so AES is this amazing, super strong lockbox. Once your data is locked up, it is incredibly safe. But, and this is a big but, this leads us to a massive problem. A classic puzzle in the world of cryptography.
Just think about it for a second. Let's say you lock a box with your secret key and you mail it to me. How do you get me the key so I can open it? You can't just put the key in an envelope and mail it, because someone could just steal that. And you can't put the key in another locked box, because then I need the key for that box. See the problem? This is the famous key distribution problem, and it's the Achilles heel of using just one key.
The solution to this brain bender was honestly a total game changer. It was a completely different way of thinking. Instead of trying to figure out how to share one secret key, some brilliant minds asked, what if we used two different keys that are mathematically linked? This was the birth of what we call asymmetric or public-key cryptography.
And here's the difference in a nutshell. Symmetric, which we just talked about, is fast and uses one key for everything. Asymmetric, the new idea, uses a pair of keys. You get a public key that you can literally shout from the rooftops. Give it to anyone. And you get a private key that you guard with your life. Anyone can use your public key to lock something, but, and this is the magic part, only you, with your secret private key, can unlock it. Boom, key sharing problem solved.
And we have to give a huge shout out to the guys who came up with this, Whitfield Diffie and Martin Hellman. Back in 1976, they developed this whole concept specifically to solve that problem of how two people who've never met can securely share a secret. It totally changed the game. Of course, there's always a catch, right? The very same complex math that makes this two-key system so secure also makes it really, really slow, like painfully slow. It's amazing for locking something tiny like another key, but if you tried to encrypt a whole movie or even just a web page with it, you'd be waiting around all day.
So now we have two tools in our toolbox. We've got our super fast AES, but it has that key sharing problem, and we've got our slow but secure two-key system that solves the problem. So what do? Well, we get clever. We use them together. This is called hybrid encryption, and it is the genius solution that powers pretty much the entire secure internet.
Here's how this beautiful dance works. First, your browser makes up a brand new, one-time use symmetric key, just for this conversation. Think of it as a temporary key. Second, it uses that super fast key to encrypt all the data. Third, it takes that tiny temporary key and locks it using the website's slow but secure public key. Finally, it sends both things over. The website uses its private key to unlock the temporary key, and then uses that fast key to unlock all the data. You get the speed of symmetric and the security of asymmetric, the best of both worlds. And this isn't some obscure theoretical process. You are using this constantly, every single day. It's the S in HTTPS. It is literally the magic that makes that padlock in your browser work. It's also used in secure email, in messaging apps like Signal, and in tools you might use to encrypt files on your computer. It is absolutely everywhere. Okay, so we're almost there. We've solved the speed problem, we've solved the key sharing problem, but there's one last crucial piece of the puzzle. When a website sends you its public key, how do you know it's really from your bank and not from some clever hacker who's pretending to be your bank? How do we verify identity? How do we establish trust?
And the answer to that problem of trust is something we call a digital certificate. You can think of it as a digital ID card, or a passport for a website. This is the final piece that makes the whole system work. Now, these certificates aren't just created out of thin air. They're issued by something called a certificate authority, or a CA. The easiest way to think of a CA is like a passport office for the internet. It's a highly trusted company whose entire job is to check a website's real-world identity. And if everything checks out, they issue an official certificate that says, yep, we verified these guys and this public key really does belong to them. Your browser comes with a built-in list of CAs that it trusts automatically.
And if you were to look inside one of these certificates, it looks a lot like an ID card. You've got the subject, which is who the certificate was issued to. You've got their actual public key. You've got the issuer, which is the CA that vouched for them. It has expiration dates, just like a driver's license. And most importantly, it has the CA's own digital signature on it, which is how your browser proves it's the real deal and hasn't been faked.
That subject field is especially important because it gets really specific. It's not just a name, it includes things like the website address, the common name, the organization, the city, the country. It's all there to make sure there's absolutely no confusion about who owns that public key.
And so that brings us to the big final thought here. This whole incredible system of online security, that padlock, your online banking, all of it, it fundamentally relies on us trusting this handful of certificate authorities. They are the gatekeepers of digital identity. And as more and more of our lives go online, it raises a really important question. Who should we be trusting with that power? Who gets to be a gatekeeper for our digital world?